Module 5.1, Exponentials and Logarithms. Objective 1, use basic graphing techniques to graph exponential functions. Objective 2, use basic graphing techniques to graph logarithmic functions. Objective 3, use laws of exponents to evaluate expressions. Objective 4, use the laws of logarithms to evaluate expressions. Objective 5, use the laws of exponents and logarithms to solve equations. And Objective 6, use laws of exponents and logarithms to solve real-world applications. In Objective 1, we're going to be able to use basic graphic techniques to graph exponential functions. As we remember back in section 1.2, the general function was in the form of f of x minus h plus k, where h represented the shift of the function to the left and to the right. Remember also that there is a minus sign in front of it. And k represents the vertical shift up and down. Fortunately, these shifts still work with exponentials. The only problem with exponentials is that there are two different formats. One where the base here is less than 1, in between 0 and 1, and the other one where the base is greater than 1. So one we have a fractional base, and here we have a base greater than 1. The basic exponential with the base less than 1, format A. Okay, so as long as it has a base here of less than 1, then they pretty much fit the same format. Their main point is going to be at 0, 1, and it'll come from here and then head down. And notice that it acts like that this is a horizontal asymptote. So the function comes down, and notice that from left to right this thing is decreasing, and that the main point for this is 0, 1. These are the two main things. So it's decreasing from left to right, and it's a 0, 1. In example 2, a basic exponential with the base greater than 1. So notice that this base right here is greater than 1. It does almost the same thing. It still has 0.01 as its point, but instead it increases, and it does this. Notice again, going to the left as it heads toward negative infinity, it's treating the x-axis as a horizontal asymptote. So this one is increasing, and its famous point or point of reference is 0, 1. Okay, now let's look at this first one. The first one, notice that this is going to be decreasing, and since the 2 is on the outside, that means it's going to be a vertical shift up. Okay, so it used to be 0.01, but now that it's shifted up to, it's going to be 0.03. And notice that it used to have a horizontal asymptote at the x-axis. Now it's moved up to. So the horizontal asymptote, or the imaginary line, is there, and this one is going to increase. This one's going to decrease. So it comes just like that, and we have graphed it. Okay. The same thing is true here. This one's going to be decreasing again. The only problem is this is on the inside of the function. It's normally where x is. And so remember, when it's inside the function, it always has a minus sign in front of it. So instead of left 2, it's going to actually be right 2. Okay, it's going to be decreasing. It's going to be right 2. So if you'll remember, the point was originally 0, 1, but now that we've moved it right 2, the point of reference is going to be there. Notice that it's just shifted left to right, so we're still dealing with a horizontal asymptote, which is the x-axis. And because this is less than 1, it's going to be decreasing. So it'll come down like this. And so our point now, since it's shifted over, is going to be 2, 1, and it's decreasing. Okay. In example 5, notice that this one is going to be decreasing again. This time we're going to have a shift, this time to the left 3, And we're going to have a vertical shift because it's on the outside, and that's going to be down 1. Okay, so it's decreasing, left 3, down 1. Okay, so the point used to be 0, 1, but now we're going to go down 1, and we're going to go left 3, so my point should be right about here. Notice that my horizontal asymptote is going to be here, because it's moved down 1, and it's going to decrease, so it should come just like this. Alright, here we're looking at example 3. Here we have a base of greater than 1. Therefore, this one's going to be increasing. And we're going to have a vertical shift of 2, up 2. Now, in these, remember we had the same point at 0, 1, but now we're going to move it up 2. We're going to have a horizontal asymptote that's one below that. And it's going to increase, so it's going to look like that. It's going to increase because the number is greater than 1. Again, because of the 3, it increases. And this time it's inside the function, so that's going to mean right 2. So it used to be at 0, 1, but now we're going to go right 2. So there's going to be my point of reference. There's my imaginary line, the asymptote, and it's going to increase. Right, and the last one, this one's going to increase because 2 is greater than 1. This means right 3, and this means up 1. So it was at 0, 1, now it's going to go right 3 and up 1. So my main point in this one is going to be 3, 2, and my horizontal asymptote is going to be right here, one below that reference point, and it's going to increase. Objective 2, be able to use basic graphing techniques to graph logarithmic functions. Again, as we remember from section 1.2, the general function was in the form of f of x minus h plus k. Here again, we have the same issue with logarithms as we did with exponentials, and that there are two different formats. We have the one where, notice that b is fractional here, and then we have the one where b is greater than 1 here. So here are the two formats. Let's look at the two general graphs. Now these two graphs are very similar to what we did with exponentials. The only difference is this is going to be increasing because of the 3. So our point, instead of 0, 1 like it was in exponentials, it's going to be 1, 0. And this one's going to be increasing. We have a vertical asymptote that runs on y for logarithms, and it increases like this. So notice that these look very similar, except they're turned. Okay? So we need to remember that this one is increasing, and its reference point is going to be 1, 0. For fractional bases in logarithms, you're going to have the same reference point. You're going to have the same vertical asymptote. The only difference is, yes, you guessed it, it is decreasing. And so it will go like this. Okay? And so notice that it's the same type of format but decreasing. Okay, here we go. Notice that we have now added 2. So this is going to be a vertical upshift of 2. This tells us that it's going to be increasing. So if our point was at one point in time 1, 0, and it's shifted up 2, it's now going to be 1, 2. We still have our vertical asymptote, and it's going to be increasing, so it's going to go like this. Okay? In this one, again, it's increasing. Again, we're going to have we have something that's inside the function, so that means we're going to go right 2. All right, so let's put, if our point was 0, 1, or excuse me, 1, 0, and I move it right 2, so here it is. That means my vertical asymptote is here, and it's increasing, so I'm going to start here and go all the way up, and it'll continue on both directions. Example 5, again, notice here we have a vertical shift which is down 2. Notice that we have an increasing function. We're going to shift left 3. So if our point was originally at 1, 0, and we're going to shift left 3, 1, 2, 3, and we're going to shift down 2, 1, 2, there's my new reference point. Our vertical asymptote is going to be 1 to the left of it, and it's going to be increasing, so it should look like that. Okay, notice that my point of reference is going to be -2, -2. All right, in these, this one means decreasing. This means down 2. Same reference point. We're dealing with 0, 1, or 1, 0, but now we're going to go down 2. So there's a point. Notice that did not affect our vertical asymptote. The only problem is this time it is decreasing. Okay. In this one, we're dealing with decreasing. We're dealing with right 3. So if our original point was 1, 0, and I go right 3, 1, 2, 3, and that means my vertical asymptote will be here. And that also means if it's decreasing, it's going to go like that. Okay, so the point here is going to be 1, 2, 3, 4, 0 will be my point of reference. Okay, and last, again, this one is decreasing. This means right 2, and this means up 3. All right, well, if my original point was at 1, 0, and I'm going to go right 2, and I'm going to go up 3, 1, 2, 3. So there's my new original point, which means my vertical asymptote is going to be here. And since it's decreasing, it's going to go like this. So my point of reference is going to be 4, 3. Objective 3. Use laws of exponents to evaluate expressions. First, we need to review the laws of exponents from algebra and show an example of each. Okay, let's first look at the laws. Law 1 is the definition of exponents. It says that a to the n is equal to a times a times a times a, and that is n times. So this is the definition of exponents. Law 2 says if you're multiplying two things with the same base, then you can add their exponents. Law 3 says that if you have n number of a's on the inside copied m times, then you will multiply n times m. So if it's power to a power, you're going to multiply them. Notice that in division, if you get a to the n over a to the m, notice the bases are the same, then you can subtract them. This law is also can be called the cancellation law. Anything to the 0 power is automatically equal to 1. And if you've got a to the negative n, the negative exponent simply means that you can drop it to the bottom, or if it's on the bottom, you can take it to the top. Now let's look at a few examples of how these work. Example 1, let's expand a to the 5th. Easy enough. This 5 means it's being copied using multiplication 5 times. Example 2, using law 2, we said that if we have the same base, then we can add the exponents. And this is also called the counting law, because if you have 4 a's here and 5 a's there, and you put them together, you'll get a 9 a's. Okay. In example 3, if you have a to the 4th to the 5th, in other words, we have 4 a's inside, and there are 5 groups of those 4 a's. So that would mean that we're going to multiply those. Example 4, if we have 8 a's on top and 2 a's on bottom, then this law states that you can subtract them. But we already know that if you have 8a's and 2a's, then 2a's are going to cancel with 2 of the 8a's, which will only leave you 6. So you can see that this is the cancellation law. All right. Any number to the 0 power is automatically equal to 1. And last, anything to the negative exponent, just remember this is understood to be under 1. Negative exponents will simply mean that we need to put it on the other side. So this will become 1 over 2 to the third, which is 1 over 8. Objective 4. Use laws of logarithms to evaluate expressions. First, we need to review the laws of logarithms from algebra to show an example of each. Okay, in this logarithm, we're able to go from logarithms to exponentials, because these are equivalent statements. Here, the identity function, where if you have an exponent and a logarithm, and they have the same base, then you just get the identical thing back. And the same thing here, log base b of b. If these two are the same number, then you get 1. Rule number 3, if you have a logarithm with the same base and they're subtracting, then you can put the two numbers together using division. Notice the subtraction division tie is kind of like exponents. If you have a logarithm with the same base and they're adding, then we can take those two numbers and multiply them together. Alright, and again, notice the tie like exponentials, where adding and multiplying have ties. And then notice in this, if we have logarithm base b of x to an exponent, we can take this in and put it out front and get n log base b of x. And last, if we have log base b of x, this is equal to a logarithm with any base of x over logarithm same base of b. So notice that you can change this, and the good thing about this one is we can use log base x over log base n or log base b, which we can put in our calculator because our calculator has the log button, and we can put it in the natural log, which is the natural log of x over the natural log of b, which is the same as log base e. So see, you can change the n to any base you want as long as they're both the same. They can be log 10 here or log e, and notice these allow us to use our calculator. Note about log base 10 logarithm and log base e, the natural log. Okay, so that is a note about these two. Alright, now let's look at an example of how each of these work. Okay, example 1, we're going to write the logarithm in exponential form using the first rule or the definition. And we can rewrite this as the base 3 to the y is equal to x. And we now have written it in exponential form. So notice that logarithms transition very easily into exponentials. Okay. In example 2, notice we have a base of 5, a log base 5, and anytime we say we had the same bases, then this would just simply be equal to 7. Here we have log x minus log base 7, so this would be equal to log of x over 7. In our next one, we have two natural logs. This is the natural log of x plus the natural log of 6. So since they're addition, we will be able to write them as natural log of x times 6 or 6x. Okay, example 5. Here we have an exponent, the 4, so we can rewrite this as 4 times the log of base 3 of x. So, and then last is what we're going to use is our change of base. So I'm going to write it as natural log of 7 over the natural log of 3. And then I'm going to break out my calculator and let's see what I get. So it's close to 1.77. Now I want you to notice that had I used log base 10 instead of the natural log, I would have still gotten the same answer. Objective 5. Use laws of exponents and logarithms to solve equations. Example 1, first thing I'm going to do is I'm going to use law 1, which is the definition, and I'm going to rewrite this as x is equal to 4 to the negative 2. So the base, and that would be the exponent. So x would be equal to 1 over 4 squared, because negative exponent needs to be dropped to the bottom. And that'll give me 1/16. So that's the first one. In the second one, in this case, I'm going to take the natural log of both sides. And then laws of exponents tell me that if you have an exponent of logarithms, I can pull it out to the front. So it'll be 2x times ln 3 is equal to ln 30. And then I'm going to divide both sides by 2 times the natural log of 3. And that should cancel those and those, which leaves me with x is equal to, and then now I'm going to break. I should get around 1.87 for this one. Okay, in example 3, I've got a 2 here that I can get rid of by dividing both sides by 2. And so that would give me log base 2 of 9x plus 5 is equal to 3. And then now I can use my exponential law. So 9x plus 5 is equal to 2 to the third power. So 9x plus 5 is equal to 8. Subtract 5 from both sides. So 9x is equal to 3. And divide by 9 on both sides. And I will get that x is equal to 1/3. And the last one, here we have a subtraction problem on one side, and the first thing that subtraction tells me is that I can probably divide. So that's going to give me log of x plus 4 over x minus 4 is equal to 1. Now remember, a logarithm that doesn't have a base is automatically base 10. So I can use my definition now stating that x plus 4 over x minus 4 is equal to 10 to the first power, or 10. I'm going to multiply both sides by x minus 4. So that should get it off the bottom. And that will give me x plus 4 is equal to 10x minus 40. I'm going to move my x's to one side, so I'm going to subtract x from both sides. So it gives me 4 is equal to 9x minus 40. And I'm going to add 40 to both sides. So 9x is equal to 44, and I'm going to divide by 9. And so x will be equal to 44 over 9. And we're done. Objective 6. Use laws of exponents and logarithms to solve real-world applications. Example 1. If 2,000 is invested at 3% compounded semi-annually, how long would it take for the investment to double? The normal formula for compound interest would be A is equal to P times 1 plus R to the nth power, where A is the amount at the end, P is the principal, R is the rate per period, and N is the number of times that is compounded. Alright, this problem takes a different twist because we're looking at our investment or our principal to double. Well, if P is our principal and we want the amount to be double P, so that would be 2P is equal to P times 1 plus R to the nth power. Okay. All right, let's go ahead and put some numbers in here. So we have 2P is equal to P times, now our rate per period, if it's invested at 3% compounded semi-annually, that would be 3% divided by 4. So it'd be 1 plus 0.03 over 4. And then the number of times, since it was semi-annually, okay, so we have 2P is equal to P, and then let's place in, we got our rate per period. So if it's twice, it's 3% twice, so it'd be 0.03 divided by 2 over, and then the number of times. Okay, well, we're not sure how many times, but we know it's going to be a number times 2. However many years times 2. So it'd be number of years times 2. Which will give us 2p is equal to p times 1.015 if I do the inside to the 2y. At this point in time, I can divide both sides by p. So that would get rid of the p's. So we're looking for 2 is equal to 1.015 to the 2y. Now what I'm going to do now is I'm going to use the natural log to get this thing down. So I'm going to take the natural log of both sides. So I'm going to take the natural log of both sides. And then I'll have the ability to drop the 2y down now using logarithm laws. So natural log of 2 is equal to 2y times the natural log of 1.015. I'm going to divide both sides by the natural log by 2 times the natural log of 1.015. And that should give me the years. So y is going to be equal to, now let's break out my calculator. Objective 6. Use laws of exponents and logarithms to solve real-world applications. Example 1. If 2,000 is invested at 3% compounded semi-annually, how long would it take for the investment to double? Alright, so normally our formula for compound interest is the amount that we have is equal to the principal that we put in plus 1 over 1 plus r to the n, where r is the rate per period and n is the number of times that it'll be invested. So the good news is we're putting in $2,000, so that would be 2,000 here. Our rate is going to be 0.03 divided by 2. And then the number of times is going to be the number of years, and since it's compounded, it would be 2 times the number of years. So like if I did it 1 year, it would be 2 times that it was compounded. And we need to make $4,000. Okay, now here I can divide both sides by 2,000. So that'll give me 2 is equal to, and then the inside of this is going to end up giving me 1.015 to the 2y. Alright, I can take the natural log of both sides, so that would be the natural log of 2 is equal to the natural log of 1.015 to the 2y. And then I would be able to bring this out in front, so that would be the natural log of 2 is equal to 2y times the natural log of 1.015. I would be able to now divide both sides by 2 times the natural log of 1.015. And that would give me the number of years. Let's break out my calculator. And I'm getting 23.2 years, somewhere in that neighborhood. So it would take over 23 years for us to do this. So if you want to do it on a full year, you would have to say 24. Example 2. The size of locust population at a time t in days is represented by the function p of t is equal to 200 e to the 0.02 t. Find the following. What is the population after 7 days? Well, the population is p of t, and we are going to find p of 7, which will be equal to 200 e to the 0.027. Now we need to make sure to put this in parentheses when we put it in our calculator. So here we're going to take, and let's break out our calculator and let's see what we get. And in this case, I'm getting 130.05, somewhere in that neighborhood. Okay, so that takes care of part A. Part B, when will the population reach 4,000 locusts? So this time we're putting 4,000 in P of T, and we are using we're going to have to figure out how to get to T. Okay, so we're going to have to do a little solving in this case. So first, let's get rid of the 200. So we're going to divide 200 on both sides. So that's going to give us 20 is equal to e to the 0.02 t. Now, I know that I can take the natural log of both sides of 20 is equal to the natural log of e 0.02. Now, I did the natural log on purpose because natural log is the same as log base e, and log base e of e will just simply cancel itself out and give us with this number. So we are left with the natural log of 20 is equal to 0.02 t, and divide both sides by 0.02. Nifty little trick there. And so t is equal to, break out the calculator once, and it'll take around 149.78 years, or rather days, because we're dealing with days up here. So it'll be 149.78 days.